This will be a short lesson on acceleration. It follows the lessons that we had on speed and velocity. A lot of you probably have a pretty good understanding of what acceleration is in real life. Okay, you pedal faster on your bike and you accelerate. Okay, in science that's pretty much the same thing too. There's just a little twist to it that we're going to add. So let's get into it. Acceleration is the rate at which velocity changes. Okay, we learned about velocity already. Velocity is speed with direction. So an object accelerates if its speed changes, its direction changes, or both change. Okay, speed, direction, or both. Okay. And that should make sense again with velocity, because velocity with speed with direction. So let's say you're in a car, you're cruising down the highway at 60 miles per hour, and you step on the accelerator. Okay, the car gets faster. Did you just accelerate? Yes, your speed changed. Okay, what if you're going down the highway at 60 miles per hour, but now you step on the brake? Did you just accelerate? Well, yes. Okay, because your speed changed. Okay, that's where it's a little bit different than kind of your normal everyday understanding. Okay, so you step on the brake, you did accelerate. Okay, let's say you're going down the highway 60 miles per hour, and you turn the steering wheel and the car turns. Did you accelerate? Yes, because direction changed. Okay, so if you change speed, or you change direction, or you change both, you accelerated. Okay, it does not mean speed up. Although if you do speed up, you're definitely accelerating too. Okay, acceleration has to have a direction because velocity did. So when you do your calculations, just like you did for velocity, make sure you put a direction on. East, west, north, south, up, down, whatever. Just make sure that you have a direction when you're doing your calculations for acceleration. Okay, how do you calculate? Acceleration is the change in velocity over time. Okay, so that's that first one here. Okay, acceleration is delta v divided by t. Delta v, the delta is just a symbol, it means change. So whenever you see a delta, it means change. Okay, so it's the change in velocity over time. Again, it should make sense. If you sped up, if you slowed down, it's how velocity changed over how much time it took to do it. Okay, the formula that you're going to use mostly is this bottom one. Acceleration is the final velocity minus the initial velocity divided by the time. Okay, so your ending velocity minus your starting velocity divided by time. Okay, that's the main one that you're going to be using. Acceleration can be positive or negative. We saw that with my example with the car. You step on the brake, you accelerate. Usually negative acceleration is called deceleration, but it doesn't have to be. Okay, it still is considered acceleration. But when you're doing your problems, if somebody slows down, okay, your answer will hopefully be a negative number. It should be a negative number. So if they're slowing down, you're going to have a negative acceleration. Okay, so let's do some examples. I was jogging at 2 meters per second east, then sped up to 8 meters per second when the dog started chasing me. It took me 3 seconds to accelerate. What was my acceleration? Okay, so again, your formula, acceleration equals final velocity minus initial velocity divided by the time. Okay, final velocity. Okay, it says I sped up to 8 meters per second. Okay, so acceleration equals 8 minus starting velocity. I was jogging at 2 meters per second east. Then, okay, so 2 was my starting velocity. Divided by the time it took me to change that velocity, and it says it was 3 seconds, so divided by 3. Okay, you do the math, we get 6 over 3, which would be 2. Okay, what's my unit label? Let's go back to the problem. Velocity was measured in meters per second, so we had meters per second divided by time, and time was measured in seconds. So meters per second per second. Okay, meters per second per second. Normally, we write that as meters per second squared. Okay, but I like this too, and we're going to talk about this a little bit, what that means. Meters per second per second. Okay, let's kind of finish the problem, and then let's talk about this. We have to have a unit, or we have to have a direction, remember, so east, and then we have to check for significant digits. Okay, in my problem, the 8 had 1, the 2 had 1, the 3 had 1, my answer has 1, so we're good. All right, circle it, and I'm done. But again, let's talk about this meters per second squared thing. Okay, what this means is every second I got 2 meters per second faster. Okay, meter per second per second. Every second I got 2 meters per second faster. Okay, that's what it means. Now you can just simply write it down as meters per second squared, or you could just write it as meters per second per second. Let's do another example. From a stop, in 8 seconds I accelerated to 5 kilometers per second west. What was my acceleration? Again, acceleration equals final velocity minus initial velocity divided by time. Okay, my final velocity was 5 kilometers per second. My initial, I said I was at a stop, so my initial was 0, divided by the time it took, which was 8 seconds. Okay, I divide that out, and I get 0.625. Okay. Remember, I need to round to significant digits. The 8 has 1, the 5 has 1, so my answer can have 1, so 0.6. Now I need to make sure I have a unit label. Okay. The 5 was in kilometers per second. The 8 was in seconds, so I have kilometers per second squared. Or again, if you wanted to do kilometers per second, that would be fine too. Alright, can I circle my answer? Not quite yet, because I have to have a direction, and it looks like west is my direction. Now I circle it, and I'm done. Okay, 0.6 kilometers per second squared west. Okay, so every second he was getting 0.6 kilometers per second faster, going west. Another example. I was running away at 9 meters per second, but slowed to a stop 3 seconds later. What was my acceleration? Okay, you know the formula, let's just fill in the numbers. Acceleration equals my final velocity. My final velocity says I slowed to a stop. So my final velocity was 0, minus my initial velocity, it says I was running at 9 meters per second. Okay, divided by the time it took, which was 3 seconds. Okay, I calculate it out, I get -3. Can I have a negative? Well, yes, I better have a negative because I slowed down. Okay, I decelerated, so I have a negative acceleration. My unit label, okay, the velocity was in meters per second. The time was in seconds, so I have meters per second, meters per second squared. Am I done? No, I have to have a direction, and it looks like my direction will be, how about away? Okay, good enough for direction. I know I have to have one, and there's my direction. Okay, so I was getting slower by 3 meters per second every second as I ran away. Okay. This picture again shows that idea that I keep stressing, what a meter per second squared means. Okay, this bike is accelerating at 1 meter per second squared. Every second it's getting 1 meter per second faster. So in 2 seconds it's going 2 meters per second, in 3 it's going 3, in 4 it's going 4, and 5 it's going 5. Every second the biker is getting 1 meter per second faster going south. This graph, I just wanted to kind of show you and see if you can figure out what happens with a roller coaster. So we look at the first part of the graph. What is that roller coaster doing in this first 8 seconds? Is it going down? Is it going up? Is it, going in straight? Okay. You see the velocity over here on the left axis and the time on the bottom axis. It's getting faster. Every second, the roller coaster is getting faster. Okay, faster, faster, faster. It's positively accelerating. So the roller coaster must be going downhill. Okay. Well, then what's happening over here after 8 seconds, 8 to 10 seconds? Well, the velocity is getting lower every second. So it's decelerating. So the roller coaster must be going up. Okay? Okay, let's do one last